Hi, and welcome to another video in fluid mechanics. Before moving on to the conservation of momentum, we will take a small break and go over a quick concept called the material derivative. This type of derivative is a consequence of our Eulerian point of view and makes up the left-hand side of what will be the conservation of momentum, or Navier-Stokes equations. Let's jump right into it. The material derivative, also sometimes referred to as the substantial derivative or the total derivative, is typically shown as capital D over dt of a quantity. To understand why it's necessary, it's helpful to start with an example. Consider a converging duct flow where flow comes in through a big opening and exits through a smaller opening. We're going to assume flow is incompressible, meaning density is unchanging, so ρ1 equals ρ2. We learned in the last video on the conservation of mass that the mass flow rate at the 2 points 1 and 2 must be equal. Mass flow rate is equal to density times velocity times area. And the densities are equal, so they cancel out, leaving us with U1A1 equals U2A2. If the inlet area, A1, is greater than the exit area, A2, then the incoming velocity must be less than the exit velocity. This change in velocity between the inlet and exit represents flow acceleration, and acceleration indicates a force must be acting on the flow. Let's see if we can identify the existence of a force through our two possible perspectives. In a Lagrangian perspective, we follow a particle along its path and we note what happens to that particle over time. So, in this case, the velocity of the particle changes in time, indicating that du dt is non-zero and there must be a force acting on the particle. Everything checks out. With an Eulerian perspective, we look at the window fixed in space and we watch particles pass by. Here, every particle we see has the same velocity, no matter how long we look at our window. This means flow is time steady, or that it doesn't change in time. In this case, the time derivative of the velocity that we measure is zero, which one would think means there's no force acting on the flow. This is wrong, and it's not because we've done anything wrong, but with an Eulerian point of view, our time derivatives need to be adjusted. Eulerian points of view have a lot of benefits, as we saw in our first lecture video of the series, but easier math is not one of them. Let's consider a non-fluids example to grasp the need for the material derivative. Consider a ball rolling down a hill. Here, we draw the ball at 3 points in time. Since gravity is acting on the ball, it accelerates, changing its velocity at the 3 points. U1 is smaller than U2, which are both smaller than U3. There is definitely a force, which is gravity, so any analysis we do should show that force. Again, we start with the Lagrangian point of view. We follow one ball and we track its velocity in time. The slope of this line is the acceleration, delta u over delta t, which is non-zero. We see a force. In an Eulerian point of view, we choose our window and fix it in space. In this case, we put our window at point 2 and we watch the balls as they pass by, noting their velocity. Let's zoom in on point 2. Also, we realize that the ball, just before it enters our window, is a little slower, and just after it leaves our window is a little bit faster. Again, if we were to look at the velocity we measure over time at point 2, we would see that it was constant. Our delta u over delta t is 0. But there is a force, and to see it we need what's called the convective acceleration. Let's add 2 more graphs to consider how the ball accelerates as it moves through space. If we were to plot the ball's velocity as a function of x and y, we would see that it does change. As the ball moves to the right, it speeds up, and when the ball's y location decreases, or means goes down the hill, it also speeds up. These lines have a slope delta u over delta x or delta u over delta y. Let's do some fancy math tricks to get things in the right units. Consider the x direction, delta u over delta t. If we were to multiply by delta x over delta x, it wouldn't matter because that's effectively equal to multiplying by 1. But now we can rearrange it. Turn this into delta u over delta x times delta x over delta t. We know delta u over delta x. We just saw that slope on our graph to the right. Delta x over delta t is the definition of the x velocity, u. So it turns out delta u over delta t is the same as u times delta u over delta x. This has the units of acceleration like we need. We can do the exact same thing to the y direction, but instead we get a vertical velocity as the product, v. These two terms are extra terms that we need when we fix our window in space. They represent the difference in velocity just before the ball enters our window and just after it exits. When we fix our observer in space via the Eulerian point of view, acceleration is defined as du over dt, which are a traditional acceleration term, plus these extra terms, which are called the convective acceleration terms. Note that the traditional acceleration term is still needed because sometimes the condition at our window changes in time, meaning it's unsteady. In the ball example, this would be like if the ramp were oscillating an angle. This type of derivative expansion applies to other quantities, not just u, and is called the material derivative. When you take a time derivative of a quantity with a fixed observation window, which is how we study fluid mechanics, you need to use this form of derivative. We will need this moving forward in the conservation of momentum, and it appears all the time in fluid mechanics. And that's it. I hope you liked this brief side video, and thanks for watching.